All right, everyone, we're going to look at some calculating rates from graphs. Again, I'm covering kind of core math skills starting off the year with. At some point, we are going to delve into a bit more sort of biology content. But I need you to cover a little bit more common ground. The aim of these live classes is not just to re-teach you content, just to go over the lessons that we have already. And because different schools doing different examples, different teachers going to be covering different things, I'm going to be circling back around to some of the biology content. But really the core that I'm trying to give you here is the exam technique, which is, as far as I'm concerned, quite separated from the content. Everyone studies content, learns content, tries to get their head around content. Hopefully with me, you're going to try to learn some of the mysteries of exam technique. Hi, Ali. Hi, Stevie. Hi, Baldwin. Pull up the chat as per usual. Oh, God, I've got all my windows split across ridiculous numbers of desktops. Let's try and consolidate this a little bit. That's a little bit better, I suppose. All right. I have put the handout on the page. I've got it on my iPad, but it's not in front of me. Okay, let's just jump straight in and do some questions, shall we? I've put probably more questions than we're going to be able to do today. Obviously, that's going to be the case always. I generally overrun, but I'm going to try to keep things more concise and give you some extra questions to have a practice at. If you get stuck on them, just ping me a question on the live classes page and we'll be good to go. Welcome, welcome, Gina. Okay, I'm just going to go straight in with the old iPad. Hopefully we're going to see some of the differences between these types of questions for calculating. Oh, okay. There's definitely some quirky things when you're using Zoom as a presenter. Resume share. Okay, great. So let's just go in straight away and analyze the question, just like we're going to do with every single one. I'm going to apply carbs. It might be useful here. We're going to have graphs. SUKU is also going to be really useful to us here. So a technician, probably good method. The effect of temperature. So that's the thing that we are changing as the experimenter. This is the independent variable on the rate of an enzyme-controlled reaction. So now we have all sorts of theory. We expect as the temperature increases, the rate of reaction increases up to a certain point, the optimum. Beyond the optimum, we're going to start decreasing the rate of reaction because the bonds are going to start breaking down. You're going to make fewer enzyme substrate complexes. So that's all sort of just like background going on in my head as I'm reading the question. Again, we're analyzing as much, pulling as much detail from the question as we possibly can. Reading the question should be hard work. Do you guys want that document actually? Do you want the link to the live class document? So feel free to bookmark this if it's useful. Okay, so again, you can just go to town there, you can create your own little bits and bobs. Throw in anything that you think is useful, that might be useful to you sitting in the exam. You want the voice of Rich sitting on your shoulder. They're the sorts of things that you can like ping down. I can see you already jumping in there. It's all anonymous, so no one can see who you are, what you are. Okay, what's next? At each temperature, he started the reaction using the same volume of substrate and the same volume of enzyme solution. My brain is now thinking, what has he not controlled? Just what immediately there, what comes up to you? You can throw that in the chat. Like, we have controlled these things, but there's plenty of things that have not been on that list, right? So we looked at a bit of this previously. Give me something to work with here, peeps. Got the same volume of substrate. What about concentration of substrate? We don't know. Same volume of enzyme. What about concentration of enzyme? What other things affect enzyme control reactions other than temperature, which is being controlled? pH could be, pH is the main one that comes to mind. Could be inhibitors. Yeah, exactly. Other things in there. What else is in the solution? We just don't know. So if we don't know, we can't draw a firm conclusion. Okay, SUKU, scale. We've got time in seconds, starting at 0. It's all linear. There's nothing too scary about that. Scale will start at 0. It's all linear. Nothing too scary about that. We've got grams per decimeter cubed. Okay, that's so fine. There's nothing too much to be worried about there. Units. Oh, I kind of covered units already. Seconds, grams per decimeter cubed. Key, do we have a key? Well, we've got them nicely labeled here. We've not got anything too much going on. U is understand. So what's the general trend? Well, I've got a very straight line relationship here, directly proportional for 25 degrees. 37 degrees, it's faster. Why is that? Well, higher temperature, more enzyme substrate complexes, more activation energy, or more collisions result in enough activation energy, then it levels off. Why? Why does it level off here? Is that because the enzyme is being used up? Well, no, it's an enzyme, it's being recycled. Is it because the substrate is being used up? Most likely, yeah, most likely. So I've already got a theory as to why this levels off. Is that useful? I don't know yet, but this is what your brain wants to be wrangling with in comprehending the graph. I've already got a pretty strong suspicion that it's the product being used up, sorry, the substrate being used up, and that's why we can't form our product. Okay. Give one other factor that, look, already, and I promise you I don't really set these questions up too much, I don't have the time for it. Like me thinking when I read the question, what hasn't been controlled, literally it's the first question. But not only does it, even if it's not a question, it's still useful to know. If we evaluate this graph, or evaluate the results, or the technician reached this conclusion, how much do you agree with it? How much do you not agree with it? Well, these are all limiting factors. How many repeats did he do? Has he done a statistical test? None of these things have been told to us. So therefore, we are sort of answering future questions by process of just understanding the question better. And it does pay dividends, because instead of getting here and then going back up to here, to go find it, you've already pretty much done the work. Okay, so I'm not even going to cover that. This is the question I wanted to look at. We've got a command word, calculate, 2 marks. That's the C of carbs, command word and marks. The rate of reaction at 25 degrees C. Now, I've already in my graph analysis noticed that this was a bang on straight line. So is the rate changing or is the rate constant? You can just put changing or constant. And if you're watching the recording, pause it, think to yourself, is the rate changing or is the rate constant for 25 degrees C? Yeah. Baldwin's come in there with constant. I've got a few more of you in there. Gina, thank you. Stevie, what do you think? You say don't know is always a valid answer. I hate it when politicians especially will just make up answers, and instead of just saying, I don't know the answer to that. And it's understandable that we don't know it all. Okay, so because it's a straight line, can anyone tell me the formula for calculating the rate of reaction from a graph if it's a straight line graph? Assuming it's a straight line graph. Exactly, so we've got the change in the y-axis, which is this one here. So change in y, that means how much has changed from here to here. So in this case, that goes from 0 to 10. So the change in y in this case is 10. If we use this full range, over the change in x, which is here, which is 240 seconds. And we probably should include our units, and it's not going to let me write off the edge of the page, divided by our change in x-axis. Now that tells us that over this period from 0 to 240 seconds, we had an increase of 10 grams per decimeter cubed. So we can then basically work that out as per second. We're going to be working what that gives us in grams per decimeter cubed per second. So this is a straight line. If I'm going to just run some different scenarios here, let me get rid of all of this. Stevie, did that make sense, what I just said there? That was quite a fast little intro. I'm just going to leave that as changing y over changing x over there. Okay, so if I'm going to draw a sketched line here, in fact, let's just use my 37 degrees. If I said, we've got 3 types of question here, I think. We've got at 25 degrees C. I'm going to do another question for at 60 seconds at 37 degrees C. And we could say during the first 120 seconds at 37 degrees C. So I've got 3 questions here, essentially. The first one is a straight line. So it doesn't matter whether we do change in Y over change in X for the first 120 seconds, because it's a straight line, it's going to go on forever, except what could you predict, is this is a separate question, predict what happens to the 25-degree line graph over the next 240 seconds. Oh, that's Ronnie, by the way. She booted her out of her maths class. I think she was going on a bit longer than had previously been planned. So predict what happens to me for this graph at 25 degrees C over the next 240 seconds. And have a think about that. Just look at, there's 2 marks, I would say. If that was a biology question, it's going to be 2 marks. It will eventually plateau. Where will it plateau? Okay, let's get rid of all these scribbles. Okay, so it's going to it's a straight line. It's going to carry on at a straight line. Is it going to carry on up here? Obviously, we would need our extended y-axis. When is it going to plateau? And this comes back to, yeah, okay, so this, why did this one plateau? It ran out of substrate. So if it had the same volume of substrate and the same volume of enzyme, then that is max. So it would be straight line up to that point, and then it's going to level off. Do you see how we can make that prediction very accurately, really? That is a strong prediction. And so that's why it would be 2 marks. Continues straight line up until whatever, we'd read that off our y-axis over here, 14 gram, products reach 14 grams per decimeter cubed, then levels off. This is where it all comes down to, like, I spent just half a second getting my head around what was going on here and why, which means that if that question comes up, I'm well prepared. I know exactly what I'm going to be writing. Okay, so now let's look at these different scenarios down here. I should probably do them in different colors. Let's do that. We've talked about rate of reaction at 25 degrees C. It's changing Y over changing X, and it doesn't matter the time duration because it's a straight line. It will be the same whether we measure it over 1 second, over 10 seconds, over 240 seconds. Now, I'm actually going to do this one as number 2, and then this one as number 3. So during the first 120 seconds at 37 degrees C, in fact, I'm going to do this in a separate color so that we can use the same graph and it not get too crazy. During first, what did I say? 120 seconds at 37 degrees C. Okay, so now what's the difference here? What's the difference here? Difference is that we don't have a straight line. It's not a straight line. I'm going to come on to tangents. Can you hold that question, Ali? And I'll come back to you in a second. But we want, basically, here, we want the average rate over this time. So I'm going to let you just do that. I'm going to give you 2 marks. Is that big enough for you to be able to see, to read the graph off? If not, let me know. I can zoom in on the graph specifically. Your 2 minutes begins now. Okay, time's up. Anyone got an answer for me? Okay, so we've got grams per decimeter cubed per second. Yeah, I mean, it is, I made this question up, right? So we haven't got very round numbers. Well, basically, how do we do this? It's during the first 30 seconds. So it is essentially, it's steeper, it's faster rate at the beginning, it's a slower rate at the end. Well, we basically just assume that this is a straight line. And we take, because we're averaging out the rate, that would give us a constant rate. And therefore, we just read this mark off here. We get 14 grams per decimeter cubed. How long did it take? Change in X is 120. So that's 14 divided by 120. So I got 0.11. I punched it in pretty quickly. 14 is the change because we're going from 0 here. Let's get rid of those scribbles. Divided by 120 seconds. So yeah, 0.116 recurring. Okay, so again, really nailing attention to the question. Now I'm going to give you the same question. What about if it's between? It doesn't have to be from 0. So this is going to be slightly more difficult. I'm going to change color again. Let's go to green. Let's say between 60 and 180 seconds at 37 degrees. These all have to be at 37 degrees because it doesn't matter at what time interval I take for the 25 degree, it's a straight line. It's going to be the same for all of them. So, okay, that's your next question, 2 minutes. I'm looking for the rate between 60 and 180, and I'll go through this one with you because it's not on the mark scheme. 2 minutes. Oh, you're not seeing what? For 37 degrees C, sorry. I paused my screen share so you couldn't see me working out the last one. So at 37 degrees. Don't worry too much about reading the numbers off the graph that accurately. I'm looking for the principle here. I'm making these questions up, so they're not going to give us the roundest numbers. Few more seconds. I'm going to resume my screen share this time so you can see. Time is up. Okay, so how do we do this? Stop. Okay, really nice, Ali. Thanks for contributing, by the way. Everyone else, you might be taking notes elsewhere. But okay, so between 60. So now we start at 60. We read up and read across. So that gives us 10 is our grams per decimeter cubed is our starting point. And then our ending point is here. So it's effectively a straight line between here and here with our change in x, change in y divided by our change in x. And this I got as 14.5. Again, I said don't stress too much about the scale. So here, the change in y is 14.5 minus 10. That's where I'm getting both of those numbers from. Gives me a change in y of 4.5 grams per decimeter cubed. And it was between 180 and 60 seconds. So 180 minus 60 gives me 120 seconds. 4.5 grams per decimeter cube divided by 120 seconds gives me this grams per decimeter cube per second. Again, we're taking an average over a section. Now, the final thing to think about, or the final type of question you could get here, is if you get a curved graph, like the 37 degrees is like not a straight line, basically. And I said, calculate the rate of reaction at 60 seconds. At that moment in time. Now, this word is really important. For the 25 degrees graph, we've got at 25 degrees, but it's a straight line. So it doesn't matter at what time interval you take here, because the change in y and change in x is constant. But on a sloping graph, on a one that isn't dead straight, we want it at a specific moment of time, what do we do? How do we do that? I'm looking for one word, basically. Stop. I didn't even start you then. So at this specific moment in time, it's a curve here. I can't do change in y over change in x when I might, it's not feasible, right? So I would need a ruler, which I've got on my desk over here. Transparent ruler, if you can see me, I don't know, I've lost my preview of myself. A transparent ruler is the best one to use because you can see through it to the graph paper underneath. Whereas an opaque ruler makes doing tangents more difficult. So you can't obviously see what I'm doing with so I'm looking at 60 seconds here. So I'm trying to match that gradient as cleanly as I can. Now, there's going to be some variation here. Some of you might draw it and you might have an angle a bit more like that. Some of you might draw it, you might have an angle a bit more like that. So there's going to be some leniency in the mark scheme. Using pencil, really, really important here, because you might draw a line and be like, actually, I don't like that. And you can see if I've drawn these three lines here and I've done that in pen, well, suddenly it becomes really difficult to read what's going on there because I've drawn over it so many times. So we're going to draw a tangent to match the slope at the point in time that the curve that the question asks us for, basically. So I think I was doing this in red. So let me see, this is my 60 line. I think something like that. So now I've got the slope at that moment in time, and now I'm looking for somewhere nice and convenient on a whole squares, ideally, where I can take this down here and this down here. Then I can work out what my change in y is, and then I can work out what my change in x is, and then I've obviously got my rate. Any questions about that? Because this might be new to some of you. But the most important thing is, yeah, you're trying to find nice, clean areas where you can read off the graph and make your life as simple as possible. I guess we could do this one if we wanted to. So change in y, we start at 5 and we get up to, this is 14. So this is 14. So 14 minus 5 gives me a change in y of 9. And my change in x is 10, what are my units here? There's 6 per small square. So that is 60, 1, 2, 3, 4. 4 6s are 24. So that's 84. I suppose if I was doing it following the logic, I would do it this way, wouldn't I? That is 96. And then that is 12. So 96 minus 12 should give me the same. Yeah. 84 is my change in X. And include your units. This is grams per decimeter cubed. This divided by this, 9 divided by 84, gives me 0.107 grams per decimeter cubed per second. So they're basically the 3 different, so for the notes probably on the Google Doc there, you've got calculating the rate of reaction for a straight line is changing y by changing X. Calculating the rate of reaction for a duration of a non-straight line, of a curved line, then we just take the average, which we basically convert it into being a straight line. So that was our examples that we did here at 2 and at 3. No, sorry, 2 and at 4. I made up an extra question. This was question 4 here. Either between or like during, you're looking for a time span. And then you just, it's the same calculation, changing y by changing X just for the period of time that's been specified. And then the additional one is calculating the rate of reaction at a moment in time of a curved graph. And obviously at that point, you're summarizing the moment in time. So you're taking that moment in time and then you're matching that gradient and you're doing a tangent at that angle. And then you do changing y by changing X for that tangent that you've drawn. They're basically all the ramifications. And I'd say notes for your doc over there, which I can see you adding to. Generally speaking, you're going to get a mark for units. Either it's going to include the units for you, but here, I'm pretty sure that one of those 2 marks, one of them is for the number that you calculate, and one of them is for the units. So, I mean, that is another skill in terms of we don't use slashes anymore. Like you see here, we've got slash seconds. If we're actually producing a rate at A level, they're going to look for, here it's grams per decimeter cubed per second. We use these negative indices to denote that. How many grams are made per decimeter cubed per second? Okay, I'm going to stop there. You have a bunch more examples here. The science behind them, you may or may not be that familiar with, but does it matter for the actual calculating? No, it doesn't matter. I mean, in terms of the graph analysis, the you of the understand might be a bit tricky. Here we've got one where it's decreasing. So we start at 10 and then we're decreasing down to a level. So our change in y would be starting at 10, and if we were doing FLASKG here, and let's say that's 8.5 or whatever that is, then it's 10 minus that number. So you just have to be a bit careful and follow it through for each question. Okay, let's just look at this. Calculate the rate of reaction in FLASKG during the first 20 minutes. Okay, so FLASKG, 0 to 20, I'm doing this. So that is I'm looking for the rate over from 10 down to there, yada, yada, yada. So again, we're just looking for those words. In this case, that's during. Calculate the rate of anti-production at day 10. Okay, so at day 10, Oh, that's actually an unusual wording in arbitrary units per day. So I'll let you have a play with that one. It's only 2 marks and it's arbitrary units per day. So I don't think that's I'll let you play with that one and you can have a go. You can ask me questions on the live class if you don't. The mark schemes are attached here as well. Calculate the rate of maltose production over the first 30 seconds. Okay, so here, 30 seconds, we've got minutes. So obviously it doesn't go to 30, but we're looking for now half a minute. We've got a little conversion to do. And so we're basically taking this dot, boom, 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 and we're doing a calculation based upon that. Again, we've got pretty regular scales here. Now this one is a great one for practicing SUKU, because what's a warning about this graph? Just a glance at this graph and I'm like, oh, okay, I've got to pay attention here. This is where using SUKU is really going to be valuable. Yeah, you've got the x-axis, you've got 2 y-axes, and you've got a key. So you've got to like marry up which bit goes with which one. So interpreting this, like, do I read this value off this side or do I read this value off this side? Question mark. I don't know. I've got to do some mental processing, and you want to do that. All of that basically is everything that SUKU is going to prepare you for, because it, like simple graphs, we don't have to worry about too much. You know, what we can see at a glance, well, this trend looks, this one is a slight lag. The peak here and the peak here is like slightly, this one goes behind. This is, you know, what's going on. Like, yeah, and we've also got this as a dotted line where the introduction of a drug has happened, like, so all sorts of things, like the peak was already coming down before the drug was introduced. So did the drug cause that? No, probably not. But what about this one? Maybe it did cause this one. So there's all sorts of things we can get from that graph without really even going too deep into graph analysis. But yeah, that's a really good one for practicing just getting your head around the graph, trying to figure out what's going on. And this will be quite slow in the beginning, but you will get much better at it because you will get a complicated graph somewhere in your paper. It's going to come up. But they are basically very much similar questions. And it's a question, it's a sort of it's a skill that students don't practice all too often. So if you get stuck with any, as I said, the mark schemes are there. I've attached to the mark scheme. So if you get the right answer, you know that you've done right. If you get stuck on something, by all means, go back and see if you can turn it over yourself, but you can ask me a question. That, yeah, that one about the antibody production, I'm going to look at that one after this and just make sure that it's at day 10 in arbitrary units per day. Yeah, do they want a tangent there? I suppose it is quite a straight line at that moment. At day 10, it is a straight line, so it's probably not. I'm going to do that one. And in fact, shall we just do it now? I can do it now if you want. I can just like, screw it. I suppose it will save questions later. Let's just have a look. So the thing that's causing me a little bit of like, not sure here, because it says at a moment in time. So let's just go from the beginning of the question for question analysis sake. Shows the concentration of antibodies, patient's bloodstream following a vaccination, yada, yada, yada. Antibody concentration 0, 100, 0, 60. Okay, scales are looking kind of normal. Vaccination takes place at day 0. Calculate the rate, antibody production at day 10 in arbitrary units per day. We've got days, arbitrary units, all my numbers match. Okay, so either we take that across there, what's that? That's 10. Well, we look at the scale here, it's like a totally useless scale, basically. We can't read very much off that. I'm just going to see if it's any different. This is a straight line. So what have we got here? It's a straight line, so you can extend it as far as you want because the gradient doesn't. Kind of challenging doing this on my iPad sometimes. Just going to extend that up there and see if now I'm looking to see, does it line up particularly nicely with any of like, I'm quite close to a nice number there, but it doesn't, not really. No, I think I'm just making this more complicated than it needs to be. Okay, let's just answer the question. I'm going to take there to there. So we've got 5, 10, 15, 20. And we've got, these are 10, so 10, 20, 30. So it's 30 divided by 20. 1.5. So what do we get if we simply were to hack it? I'm just switching color. And if I just read that across here, what is that? This is 10. So this is about roughly 8. But I mean, at that scale, I don't think it's 8 over 10 days. Yeah, so that doesn't feel right to me. I just check the mark scheme so I can make sure that I am right on this and I haven't just left you confused. Oh, I was doing it on the mark scheme. Protractor, no, you don't need a protractor on the exam. In fact, you can check what it says on the front cover of your exam papers when you're printing off past papers. It's like pen, calculator, pencil, rubber, ruler. I think that's pretty much, you don't need a protractor for sure. 1.5. Allow plus or minus 0.02 because the angle that you read this off, it is pretty straight here, so it's an easy one to do. It's not actually curving. But the reason, do you see why I wasn't 100% sure there? Because it said at day 10. So it's the rate that we want at that moment in time, not over the first 10 days. In which case it would have been the one that I did in red. You would have read this across. And this was roughly 8. And then this would have been 10. So over the first 10 days, the rate would have been 0.8 arbitrary units per day. But at day 10 is this line here. Does everyone see the difference? And it wasn't immediately obvious to me just glancing at that question, which one I should use. But by doing the question, I basically figured it out. So it's really important that we pay attention to the very specifics of the question there, because you will get a different answer if you do it differently. If I put during the first 10 days, we get this answer. At 10 days, we get the other answer. Any questions, or are we good? I will see you all tomorrow.